Welcome students. In this part we are going to see about the stoichiometry and stoichiometric calculations that is involved in a chemical reactions. So we are dealing with the chapter Some Basic Concepts of Chemistry, chapter 1 of class 11. So in this part we are going to see about stoichiometry and stoichiometric calculations. So what is stoichiometry? Stoichiometry is nothing but stoichiometry means the calculation of masses of reactants and products involved in a chemical reaction. So we know that in a chemical reaction we have reactants that combine to give products. So from the laws of chemical combination we know that the masses in a chemical reaction is neither created nor destroyed in most of the cases. So these masses that is involved in a chemical reaction can be either reactants and products. So it is important for chemical companies to calculate them appropriately in order to find out what are the reactants that are formed and what are the products of reactants that are consumed, how much is consumed and how much product is formed. All these calculations comes under stoichiometric calculations. So stoichiometric calculations are done based on or are done using the balanced chemical equation. So in the lower classes you might be familiar with balancing of chemical equation. In this class 11 we will not teach balancing. So I hope you all will know the balancing of chemical equation. Clear? So stoichiometric calculations is strictly based on this balanced chemical equation. Clear? So first of all what we have to find out is what are the informations that are obtained from a balanced chemical equation. What can you gather? What informations can you gather from a balanced chemical equation? That's what we are going to see in the next slide. So information from a balanced chemical equation. So for that we are going to consider a chemical reaction where methane is undergoing oxidation or combustion reaction. Combustion means oxidation reaction. So what is the formula of methane? CH4. Combustion means CH4 combines with oxygen. So CH4, which is a gas, combines with oxygen, 2O2 gas, giving carbon dioxide plus 2H2O. Clear? So methane combines with oxygen to give carbon dioxide. So this is one of the fuel that you will see in liquefied petroleum. So this is CH4 plus 2O2, again gas. So the entire species involved in the reaction is gas. And if you look, you can see that this equation is very well balanced. So this is a combustion equation and it is balanced. All the species is given here is already balanced. What are the information that I am going to get from this balanced chemical equation? So if you consider the number of molecules, in very simple terms you can say that from the balanced equation you will know that information. One molecule of methane, if it reacts with 2 molecules of oxygen. So one molecule of methane, if it reacts with 2 molecules of oxygen, what are you getting? You will get 1 molecule of carbon dioxide and 2 molecules of water. 1 molecule of carbon dioxide and 2 molecules of water. So this is the first basic information that you are getting. So you can say it in another way around. If you want to get 1 molecule of carbon dioxide and 2 molecules of water, you need to supply 1 molecule of CH4 and 2 molecule of oxygen. So this is the first information. Instead of that, if I am taking 100 molecule of CH4, so instead of 1 molecule of CH4, if I am taking 100 molecule of CH4, how much molecules of oxygen is required? 200 molecules of oxygen. So if that is the case, if this is 100 and if this is 200, how much carbon dioxide will I get? I will get 100 molecule of carbon dioxide and 200 molecule of water. So that's what you will get. So I am again increasing the number. 1000 molecule of methane, then I have to add 2000 molecule of oxygen in order to get 1000 molecule of carbon dioxide and 2000 molecule of water. Again I am increasing 6.022 into 10 raised to 23 molecules of methane. So what is this value? 6.022 into 10 raised to 23, that is 1 mole. So 1 mole of methane, then how much I have to take here? 2 moles of oxygen, giving 1 mole of carbon dioxide and 2 moles of water. Clear? So since again it's a number of molecules, but here it was only 1 molecule, here I am talking about 6.022 into 10 raised to 23, which corresponds to a number which I can write as 1 mole. So if I take 1 mole, that is 6.022 into 10 raised to 23 molecules, then how much is required in the case of oxygen? It is 2 moles, that is 2 into 6.022 into 10 raised to 23. So then I will get 1 mole of carbon dioxide and 2 mole of water. So what is the mass of 1 mole of CH4? What is the mass of 1 mole of? So 1 mole of CH4. So 1 mole of CH4 means it's the mass of 1 mole. It's called molar mass. Clear? So it's called molar mass. What is the molar mass of CH4? How to find the molar mass? You just take the molecular mass and convert or express it in grams. So carbon is 12 plus 4. There are 4 hydrogens, so total 16 gram. So instead of 1 mole of methane, I can write it like this: 16 gram of methane, 2 mole of oxygen. 1 oxygen is 16 into 60, 16 plus 16, 32. We have 2, that means that 4 16s must be, so 4 oxygen atoms must be there, so it is 64 gram of oxygen. Then carbon dioxide, 12 plus 16 plus 16, that is 44 gram of carbon dioxide plus 36 gram of water. So now it is meaningful. If you are looking into the mass, you cannot directly translate this into mass, like how I translated this into, like looking into the coefficient here. What is the coefficient of CH4? It is 1. This is what we call as coefficient. For oxygen, the coefficient is 2. For carbon dioxide, coefficient is 1. For water, the coefficient is 2. Clear? So looking into the coefficient, I can predict, or I can find out easily the number of molecules that I will consume and the number of molecules I will get. Also I can calculate number of moles and molecules using the coefficient. But to know the to calculate the mass, I must know the molar mass. Then I can equate them. 16 gram of methane, if I am adding with 64 grams of oxygen, I will get 44 grams of carbon dioxide and 36 gram of water. So according to the law of mass action or law of conservation of mass, you can see that on both sides of the equation, the mass remains the same. Clear? Okay, let's take this into the next step, next level. So we have the balanced equation, and from this balanced equation we now know that 1 mole of methane and 2 mole of oxygen from this coefficient. This is a stoichiometric equation and this is called stoichiometric coefficient. So from this stoichiometric coefficient, what is coefficient? It's the number of molecules or number of moles of molecules that is taking part in the reaction. So from this stoichiometric coefficient, I can calculate the number of moles involved, or I can equate them. So if I am applying Avogadro's law, What was Avogadro's law? Avogadro's law was saying that equal uh, volumes of all the gases at same temperature and pressure contain equal number of molecules. Equal volumes of all the gases at same temperature and pressure contains equal number of molecules, or the other way around. Equal number of molecules of same of different gases at same temperature and pressure will occupy same volume. So you can make this Avogadro law the other way around, that says that if the number of molecules is the same at same temperature and pressure, then the volume occupied by the same number of molecules will be the same. So here you can see it is 1 mole, and this is also 1 mole of gas. So we can see that this is gaseous system. Here it is 1 mole of methane, here it is 1 mole of carbon dioxide. Doesn't matter if the number is same. So here the number is same, 6.022 into 10 raised to 23. That means that their volume should also be the same, must also be the same. And what about this? Here the volume is double because the number of moles, number of particles is double. Here also the same. Clear? So let's see. We can translate it like this: 1 liter of methane plus 2 liter of oxygen giving 1 liter of carbon dioxide plus 2 liter. So the basic unit what I took was liter. So since I took liter here, I can get the other liters easily from this stoichiometric coefficient. How did I apply it? By applying, what did I apply it? By applying Avogadro's law for the gaseous system. Now again, so what is the volume of 1 mole of a gas at standard temperature and pressure? What is the volume of 1 mole of a gas at standard temperature? What is the standard temperature? 0 degrees centigrade, or you can say 273 Kelvin approximately. So the precise value of this temperature 0 degrees centigrade in Kelvin scale is 273.1 5 Kelvin. So this is 273.15 Kelvin. But for sake of calculation, easiness of calculation, we take round the figure as 273 Kelvin. So 0 degrees centigrade means 273 in Kelvin scale. 0 degrees 273 Kelvin. And the pressure is 1 bar. So normally when you express pressure, we express in 1 atmosphere. Clear? But here it is the unit recommended by SI system, or International Union of Application. So Applied and Pure Chemistry, it's an international body. They recommend this as the standard units for temperature and pressure. So it is 273 Kelvin and pressure 1 bar. Actually the standard unit is Pascal, but we use here 273 Kelvin and pressure 1 bar. Clear? So this is called as STP, standard temperature and pressure. So the question is, what is the volume of 1 mole of gas at STP, at standard temperature, that is 273 Kelvin and pressure? So according to Avogadro law, they are saying that temperature and pressure should be the same. So we are fixing that temperature and pressure 273 Kelvin and to 1 bar. What is the volume of 1 mole of gas? So according to Avogadro law, equal number of molecules at standard temperature and pressure occupies same volume, isn't it? Equal number of molecules at standard temperature and pressure occupies same volume. So here we have 1 mole of gas. If the temperature and pressure is fixed for all gases, the volume should be the same. For all gases, volume of 1 mole of gas must be the same according to Avogadro's law, and they tried to find it out, and the value was 22.7 liters. At STP, volume of 1 mole of gas is 22.7 liters. It's an important value. You will need this especially for the entrance calculations. So volume of 1 mole of gas is 22.7. So what is STP? Standard temperature and pressure, and its value is given here, 273 Kelvin and 1 bar. Clear? So again, we are using the same formula. So I have 1 mole. So instead of 1 mole, now I can substitute the value of volume here. So I have for 1 mole 22.7 liter of methane, and 2 mole it's a double of 22.7, that is 45.4 liter. 22.7 liter of, so instead of 1 mole I can write again, and here I can write again 45.5 or 45.4 liter, the double. So this is after applying Avogadro's law for the gaseous system. Now using this stoichiometric calculation, I am going to do few calculations. Let us see. Calculate the amount of water produced by the combustion of 25 gram of methane with a sufficient supply of oxygen. So the question is again based on the same formula. Combustion of methane means CH4 plus 2O2 giving CO2 plus 2H2O. So we have the balanced equation. So what they are asking is that how much amount of water is produced if I am using 25 gram of methane. What I know from the stoichiometric calculation is that molar mass of methane is 16 gram and 2 into molar mass of O2 is 64 gram will give 1 mole of CO2. Its mass is 44 gram, and water it is 18 gram, molar mass into 2 is equal to 36 gram. So using the stoichiometric calculations or using the balanced equation, I can equate the things like this. Clear? Now what they are saying is, if I am using 25 gram, if I am using 16 grams, how much water will I get? I will get 36 grams. Clear? If I am using 16 grams of methane, I will get 36 gram of water. So what they are asking is, how much water will you get if you are using 25 gram? Using 16 gram, you will get 36. So if you are using 25 grams of methane, how much water you will get here? So what is the standard step? What you have to find out is, if I am using 1 gram of methane, how much water I am getting? First what you have to find is, if I am using 1 gram of methane, how much I am getting? So for that, amount of water formed from 1 gram of methane, what do you have to do? So what is the thing that you have to find out? You should go to the numerator. So it's like this, 36 by 16, that is equal to 2.25 grams. So by using 1 gram of methane, you will get 2.25 grams. So whatever thing you want to find out, you put it in the numerator. So here you have to find out amount of water. So you put it in numerator. The other unit you put it in the denominator. So 36 by 16, which is equal to 2.25 gram. This is how you want to remember. You can remember like this, like whatever thing you want to find out, you put that thing in the numerator, the other one in the denominator. When you convert the value into unity, so you're converting the value into unity, into 1 gram. Amount of water formed from 1 gram is equal to 36 by 16, 2.25. So for 1 gram you will get 2.25 gram of water. So for 25 gram, how much you will get? You just multiply it with 25. 2.25 into 25, which is equal to 56.2 gram. So this is how to do this calculation. There is an alternate method to do this calculation. So either you can use this method or you can use the method that I am going to tell in the next slide. For some, it is the best method. For some, this is quite fine. So let us see. Knowing both methods is good because it's always an advantage. You can be flexible. Okay. So again, I am using the same problem to demonstrate the other method. So from this stoichiometric calculation, I have also another one, that is, instead of taking mass, I can take the number of moles. Clear? So 1 mole 2 mole, 1 mole, 2 mole. It's more easier than the mass. Okay, so what they have asked is, if I am using 25 grams of methane, how much water is produced? So one thing I know is 1 mole of methane will give 2 mole of water. 1 mole of methane will give 2 mole of water. Clear? So if I am taking a particular quantity, I will get double amount of water. Comparing to the methane, I will get double amount of water. So what I have to find out? Just I will find out the number of moles present in this 25 gram. How many moles of methane is present in this 25 gram? For that I will apply the formula that is connecting between number of moles, mass and molar mass. Let us see. So number of moles of methane in 25 grams is equal to, I am applying the formula, number of moles is equal to N is equal to W by M, mass divided by molar mass, which is equal to mass is given, that is 25, divided by molar mass, that is 16, which is equal to 1.56 mole. Clear? So this much mole of methane is in 25 gram. If 1 mole of methane gives 2 mole of water, 1.56 mole of methane will give its double, that is 1.56 into 2, that is 3.12 mole. Clear? So from this stoichiometric calculation, you can easily apply that, isn't it? 1 mole gives 2 mole. So 1.56 mole will give its double, that is 3.12 mole. Now what I have to do? I have to find out how much mass of water is present in this 3.12 mole. So I will just multiply with molar mass. 3.12 mole into molar mass of water, that is again 56.2 grams. So this is another method. In the previous slide what you saw was a different method using directly the mass. Here I am just converting mass into mole, and at the end I am converting back that mole into mass again. But for some people this looks very simple. Let's look another example, another problem. How many moles of methane are required to produce 25 gram of carbon dioxide after combustion? So this is again based on the same equation. So we have the equation. What's the question? How many moles of methane are required to produce 25 gram of carbon dioxide? So they have asked in moles and they have provided something in gram. So it's always easier to find or use the method in moles. Let's see. So 1 mole of methane, again we have that stoichiometric calculation, stoichiometric coefficients here, and they have asked amount required to produce 25 gram of carbon dioxide. So again the ratio is that if I use a particular quantity, I will get double the amount of water in moles, isn't it? So if I'm using 1 mole of methane, I am getting 2 moles of water. What I have to do is I just calculate the number of moles in this carbon dioxide. For that, number of moles of carbon dioxide in 25 gram of carbon dioxide is, I have the formula, I just substituted 25 divided by molar mass of carbon dioxide is 44, which is equal to 0.57 mole. So it is 0.57 mole. 1 mole of methane gives 1 mole of carbon dioxide, isn't it? 1 mole of methane gives 1 mole of carbon dioxide. So here what I got is 0.57 mole of carbon dioxide. So how much mole of methane should I use? It's the same, because here if I use 1 mole of methane, I am getting 1 mole of carbon dioxide. And in this reaction what they said I got is 0.5 mole. So how much methane would have they used for combustion? It's the same, it is 0.57 mole. Clear?